Hello, calculus students. Let's work through our review in preparation for our next test. So we'll jump right into number 1 that says, find all values of k for which the integral from 1 to k of x dx equals 7.5. So what we're going to do is use our fundamental theorem of calculus. Let's find the antiderivative of x. The antiderivative of x is x squared over 2. And then we're going to evaluate that antiderivative at k and at 1, and then set that equal to 7.5, and that way we'll be able to solve for k. So the first thing we're going to do is we're going to take k and we're going to put it in for x. So that would be k squared over 2. And then minus, now we're going to take 1 and put it in for x. So that would be minus 1/2, and that's all equal to 7.5. Okay, and at this point, you might want to simplify this equation a bit. Remember, whenever there's an equation that involves fractions, you can always multiply through by a least common denominator and get rid of those fractions. So we're going to multiply every term on both sides by 2 to get rid of those fractions, and we'll have k squared minus 1 is equal to 15. Then we'll add 1 to both sides and get k squared is equal to 16. So our solutions then would be k equals plus or minus 4. And then problem number 2 says, find f of 9 if the integral from 2 to 9 of f prime of x dx equals 17 and f of 2 equals negative 4. So you should recognize this from class as a time that we're going to use our net change theorem, where we get our final amount. The final amount will be equal to the initial amount plus the change, which the change we'll find the change by taking the integral from that initial amount to the final amount of f prime of x dx. Remember, when you integrate a rate, that gives you an amount. So our final amount then is that we're looking for, we're trying to find f of 9, okay, given an initial amount, which is f of 2, and then plus the change, which is that integral from 2 to 9 of f prime of x dx. Now on the test, you will not need to write this line. I'm just writing it out so you know where all the numbers come from. So f of 9 is what we're looking for. All right, f of 2 we're given, it is negative 4, and then we're told that the integral from 2 to 9 of f prime of x is 17. So we'll put that in here. So f of 9 then is negative 4 plus 17, or 13. Okay, number 3 says, given the graph of f prime and an initial value of f of 0 equals 5, we're going to find f of 2, f of 3, and f of 6. So let's start with finding f of 2, and f of 2 will be equal to that initial value of f of 0 plus the integral from 0 to 2 of f prime of x dx. All right, so that would be, let's see, f of 0 we're told is 5, and then we need to add to that the integral from 0 to 2 of f prime of x dx. So we're looking at the graph of f prime, so that integral will be the area between the graph and the x-axis from 0 to 2. So using your geometry formula, this is a triangle. If we take 1/2 its base times its height, this area is 1. So f of 2 then will be 5 plus 1, which is 6. All right? And then moving on to f of 3, okay, f of 3 is going to be f of 0 plus the integral from 0 to 3 of f prime of x dx. So now as we find that area between the graph and the x-axis, from 0 to 3, we know from 0 to 2 is 1. And then if you look at these two areas between the graph and the x-axis, one of them is above the x-axis. Let's see, let me try this in. One of those areas is above the x-axis, and then one is below. Now, they have the same area. They both have an area of positive 1/2, but since one is above the x-axis and one is below the x-axis, the value of the integrals would be opposite. So these two integrals, values of the integrals, cancel each other out. So that means f of 3 is going to be the initial value of 5 plus 0, which is, I'm sorry, not 5 plus 0. I forgot about the area. I was concentrating on these two regions, and I remember we're finding the area from 0 all the way to 3, so it's going to be 1 plus these two areas 0 out. So 5 plus 1 equals 6. All right? And then finally, to find f of 6, that would be equal to f of 0 plus the integral from 0 to 6 of f prime of x dx. So that's going to be 5 plus, now let's talk about the area between the curve and the x-axis from 0 all the way to 6. Well, remember from, let's see, 0 to 3, that was a total of 1 because these areas canceled each other out. Then all this area under the curve, let's see, and there's lots of ways that you can do this. I'm just kind of piecing it together. So this area under the curve is also going to have a negative integral. This area above the curve would be positive. So I guess one way we can look at it is these two areas cancel each other out, okay? These two areas canceled each other out. And then we had an area of positive 1 up here and an area of negative 1 down here. So that means the net change from 0, so all of this area cancels that area. So the net change from 0 to 6 then is 0. So our final answer then would be 5 plus 0, which is 5. Now let's look at problem number 4, which says, selected amounts of rain in centimeters in a rain gauge. So let me stop here and just say, I'm using this word amount loosely. Obviously, when we measure an amount of rain, it would be an amount of volume, which would be cubic centimeters. But when you think of a rain gauge, if you've ever seen a rain gauge, it's like a little tube, and it measures how many inches or how many centimeters of rain has fallen. Just like on the news, when you hear the amount of rain has fallen, they're not going to say so many cubic inches. They give it in inches. So when I say amount, I mean, I guess I'm talking about the height of the volume is what I'm talking about. Okay, so selected amounts of rain in centimeters in a rain gauge after 10 minutes are shown in the table below and is given by the differentiable function r of t. So here's our selected values. So for any time t, this would be the height of rain in that rain gauge. So letter A says, evaluate the integral from 1 to 12 of f prime of t dt and explain its meaning in context of this problem using proper units. All right, so first of all, r of t is an amount function. It tells us how much rain is in the rain gauge, or how many inches or centimeters have fallen. Okay, this is the derivative of r of t. So if which would be the rate at which the rain is falling in centimeters per, what are we measuring in centimeters per minute. All right, so when we integrate this rate, that gives us the amount of rain that has fallen from 1 to 12. So if we use our fundamental theorem of calculus then to find the integral from 1 to 12 of r prime of t dt, what we're going to do is take the antiderivative of r prime of t, which is r of t. We're going to evaluate that at 12, and then evaluate the antiderivative at 1, and then we'll subtract those two amounts. Well, those amounts are given to us in the table. R of 12 is 4.2, and R of 1 is 1.1. So we just need to take 4.2 minus 1.1, and we get 3.1. Now, let's talk about the second part of this problem, because you want to make sure you answer the whole question. It goes on to say, explain the meaning of this answer in context of the problem with proper units. So in class we've used the little mnemonic device woo-woo, okay, it's a W, woo-woo, which stands for what with units, when with units. So what are we talking about? We're talking about an amount of rain. So what this answer means, it means it is the amount of rain in the rain gauge. So what this answer means, this integral from 1 to 12 of r prime of t d. Oop, I forgot my dt. Oh, mercy, let me change that. I hope you guys noticed that. Anytime you write an integral, it's almost like parentheses. If you have a left parenthesis, you should have a right. Well, anytime you have an integral symbol, you should have a d variable statement. So sorry about that. Okay, so back to what we were talking about. 3.1, what does that represent? Well, this integral represents how the amount of rain in the rain gauge changed from time t equals 1 to 12. So let's write our answer like this. Let me erase what I have here. Let me get rid of that. Sorry about that mess. Okay, so what we're going to say is we're going to say that the amount of rain in the gauge, the amount of rain in the rain gauge, let's see, G-A-U-G-E. Okay, now what did it do? It changed, didn't it? And I would use the word change. I wouldn't use the word increase or decrease. Let's let the number, the numerical value, tell us whether it's an increase or decrease. If it's an increase, it'll be positive. If it's a decrease, it'll be negative. So we're going to say the amount of rain in the rain gauge changed by 3.1. Now, 3.1, so the amount of rain in the change of the amount of rain in the rain gauge is the what. Now, the units would be the 3.1 centimeters. So that's our first woo. Now we need to say when with units. So the simplest way to say that is just say from t equals 1 to t equals 12. So that's the when, and then don't forget your units, minutes. Now for part B, I didn't quite ask what I meant to ask, so let's talk about what the question that's actually asked here, and then we're going to do a follow-up question of what you'll actually see on the test. What I typed here was explain the meaning of 1/11th of the integral from 1 to 12 of r prime of t dt in context of this problem using proper units. So remember, r of t is an amount function. R prime of t would be a rate function in centimeters per minute. So the answer to this question would be the average rate in centimeters per minute, so from time t equals 1 to time t equals 12. So if you were asked this question, the answer would be an average rate. The question I meant to ask was this. So what you'll see on the test is explain the meaning of 1/11th, which, by the way, in case you're wondering where that 11 came from, that 11 is the b minus a, the upper limit of integration minus the lower limit of integration, so 12 minus 1. So what you'll be asked on the test is explain the meaning of the integral 1/11th of the integral from 1 to 12 of r of t dt. Now, r of t, remember, is an amount function. So while this expression is giving us an average rate in centimeters per minute, this expression would be giving us an average amount. So the answer to this, in context of this problem, with proper units, this expression represents the amount of rain in the rain gauge, how do you spell gauge? G-A-U. Never spell it right. Okay, and the amount of rain in the rain gauge. Now that's the what. Give the unit, say in centimeters. Okay, then let's talk about the when from t equals 1 to t equals 12, and then don't forget the time units, which would be minutes. And then you might have noticed I left out a really important word. This is the average. The average amount of rain in the rain gauge in centimeters from time t equals 1 to t equals 12 minutes. Numbers 5, 6, and 7 on our review are problems about the second fundamental theorem of calculus, which really shows us how derivatives and integrals are inverse operations. They undo each other. So let me just go ahead and work this out the long way. Now, you don't need to write this down, and this will not what you'll be asked to do on the test. And also, this has been in your notes, but I just want you to see it one more time of what it means to take the derivative of the integral from 0 to x of a function of t dt. So first of all, let me just remind you that the fifth root of t is the same thing as t to the 1/5, right? So what we're going to do is we're going to take the derivative of the integral from 0 to x of the fifth root of t dt. So the antiderivative of t to the 1/5 would be, let's see, t to the 6/5 divided by 6/5. So that's 5/6 times t to the 6/5. And then we're going to evaluate that antiderivative at 0 at x, and then we will subtract those. So this would be the derivative of, let's take x and put it in for t. So that would be 5/6 t to the, I'm sorry, not t, x, 5/6 x to the 6/5, and then minus 5/6 times 0 to the 6/5, which will zero out for us. All right, and now when we take the derivative of that expression term by term, remember when we take derivatives, we're going to take this exponent, bring it around front, and multiply it by the coefficient. So 6/5 times 5/6 cancel each other, and we just get x. And then remember, you reduce the power by 1. 6/5 minus 1 is 1/5. And then, now this constant happens to be 0, but no matter what this constant is, when we take the derivative of that constant, we would get 0. All right, so that means this is what we get when we work it out the long way. So all that to say, you can save a lot of time. You don't need to do this every time. All we need to do is take this upper limit of integration, which is x, and replace t with that x. So our final answer is just the fifth root of x. And then number 6, now this one's a little bit different in that this time the upper limit of integration is a function of x. It's not just x. So you have to use the chain rule. So you're going to do two things. You're going to replace t with this upper limit of integration, which is a function of x, and then you're going to multiply by the derivative of this upper limit of integration. So I'm going to go ahead and do that part first. What is the derivative of cosine x? Well, the derivative of cosine x is negative sine x. So that's the chain rule part. And then times 1 over, we're going to replace t with cosine x. And that's all there is to it. Now, we can simplify this a little bit. A couple things we can do. Number 1, we could rewrite it as negative sine x over cosine x. And then don't forget your trig identities. If this were a multiple choice question, that might not be how you see the answer represented. It might be simplified or rewritten as negative tangent x. Remember, sine x divided by cosine x is tangent x. Now in number 7, there's a couple things we need to notice up front. The first thing we need to notice is the bounds of our integral are backwards. To use the second fundamental theorem of calculus, the upper limit of integration needs to be x. Here it's the lower limit of integration. So quick fix to that is we can just take the opposite of this integral and we can turn those bounds around. Another thing to notice is this constant of 3. Now, a constant can be brought in front of an integral symbol, and it also can be brought in front of a derivative symbol. So we're going to pull that 3 all the way in front, and then remember, since we're switching these bounds, we also need a negative. So we're going to rewrite this as negative, we're going to rewrite it as negative 3, the derivative of the integral from, now we're switching the bounds, so it's 1 to x. The reason we're switching those bounds again is because we put the negative out front, of e to the t dt. So now all we need to do is replace it's called the dummy variable, replace this t with x. So our final answer will be negative 3 times e to the x. So we'll write it like this, negative 3 e to the x. And that's our final answer. In this next section of the review, we're going to get a bunch of practice with simplifying or finding indefinite integrals that involve u substitution. So let's talk about when you want to use u substitution. Well, you usually are going to use it if you see a situation like this where you have a function within a function. That's called a composition of functions. So we have something being raised to the 5th power, and what's being raised to the 5th power? Well, a function of x. So this is a good time to use u substitution, and what you want to choose for u is that inner function, okay? So we're going to let u be x squared minus 1. Then du would be 2x dx. So now we will rewrite the integral in terms of u. So the first thing we want to note is that this x squared minus 1, that can be replaced with u. And then the x dx we can replace with du, except that du is 2 times too big, okay? So we could replace x dx, it could all be replaced with du, except that we have this factor of 2 that we need to take care of. So the fix for that is we just need to put a 1/2 out in front of the integral, and that will balance things out. So we would have the 1/2 the integral of, now the yellow is being replaced with x squared minus 1, and then notice what's happening to the yellow. It's being replaced by 5. I mean, not replaced, it's being raised to the 5th power. So if we're going to replace x squared minus 1 with u, then we need to raise u to the 5th power. So this would be 1/2 the integral of u to the 5th, and then all the blue stuff, the x dx, can be replaced with du because we put the 1/2 out front to balance out this 2. So that would be du. All right, so now we will just find the antiderivative. So that would be 1/2 u to the 6th over 6. And then since this is an indefinite integral, don't forget your plus c, because the answer to an indefinite integral is a family of functions that all have the same derivative, or actually be this derivative. So don't forget, if you don't see bounds, make sure you have a plus c in your answer. So then we just have one thing left to do, and that is we need to back substitute. We're going to go back and replace u with what we said it was equal to. It was equal to x squared minus 1. So our final answer will be 1/2 x squared minus 1, all raised to the 6th power over 6 plus c. And then I guess that's not our final answer, because of course we could simplify that a little bit and rewrite it as x squared minus 1 to the 6th all over 12 plus c. That can be our final answer. And then in number 9, I hope you can see that this is another composition of functions. Notice we have a square root function, but what is the radicand? What's the inside of that function? It's another function of x cubed plus 4. So this inner function is what we're going to choose for u. We're going to let u be x to the 3rd plus 4. Then du will be 3x squared dx. All right, so let's talk about replacements. We can replace this x squared plus 4 can be replaced with u, and then the x squared dx we can replace with du, except that notice that there's this extra factor of 3 here. So du is 3 times too big, so to make the replacement we're going to have to balance it out by putting a 1/3, oops, that's not what I meant to do, putting a 1/3 out in front of our integral. So that would be 1/3 the integral of, now we're replacing all the yellow stuff with u, and what's happening to the yellow stuff? We're taking the square root of that. And then remember, if we're going to have to find an antiderivative in a minute, it's going to be easier if we write this radical as an rational exponent. So this would be 1/3 u to the 1/2 power, because the square root of u is the same thing as u to the 1/2. And then we're replacing x squared dx with du, as long as we put the 1/3 out in front, since du was 3 times too big. So that would be du. All right, so now let's find the antiderivative. So that would be 1/3 times, let's see, it would be u to the 3/2 divided by 3/2. So that's 2/3 u to the 3/2, and then don't forget your plus c. Now I'm going to take a minute. If you want to fast forward this part, you can. I just want to make sure everybody knows where the 2/3 and the 3/2 came from. We're using the power property, u to the n. If we're going to find the antiderivative, that would be u to the n plus 1 over n plus 1. So if we're finding the antiderivative of u to the 1/2, then that's going to be u to the 1/2 plus 1 over 1/2 plus 1. So simplifying, 1/2 plus 1 is 3/2. And when we are dividing by 3/2, dividing by 3/2 is the same thing as multiplying by the reciprocal. So that's why it's 2/3 u to the 3/2. All right, so back to our problem. Then let's go ahead and we'll do a couple things. Let's back substitute u. We're going to put x cubed plus 4 back in for u, and then also we can do a little bit of arithmetic here. So our final answer would be 2/9 x to the 3rd plus 4 raised to the 3/2 power, and then plus c. So number 10 gets a little bit more interesting. I think by now you know what you want to choose for u. It's this inner function of 3x plus 1. So let's let u be 3x plus 1. Then du would be 3dx. So when we go to make replacements, we can replace the 3x plus 1. That's going to be replaced with u, okay? And then dx can be replaced with du as long as we balance it out. We've got du is 3 times too big, so as long as we put a 1/3 out in front, then du can be replaced with dx. So, but there's one thing left to be that we need to make a substitution for, and that is this x. All right, so what can we do there? Well, remember that here we have an expression of u in terms of x, so we can take this little equation, we can solve it for x, and then we'll have x in terms of u, and we can make a replacement then for this x. So let's go ahead and do that. So if u is equal to 3x plus 1, and I want to solve that for x, I'm going to subtract 1 from both sides, and we'll get u minus 1 equals 3x, and then I'll divide both sides by 3. So I'm going to turn this around and say x is equal to u minus 1 over 3. So now when I go to rewrite this this whole integral in terms of u, I have something to put in for x. So here's what it's going to look like in terms of u. Well, first of all, remember that du was 3 times too big, so we need to put a 1/3 out in front. So it's going to be 1/3 the integral of, I'm going to replace x, remember, gets replaced with u minus 1 over 3. So that's going to be u minus 1 over 3 times, the yellow is being replaced with u power, so that's going to be u to the 4th, and then dx is being replaced with du, and we can do that because we put the 1/3 out front. Whew. Okay, now let's clean this up a little bit. First of all, I can multiply the constant, so I'm going to pull this 1/3 out in front, multiply it by the 1/3 that's already there, so that would make it 1/9, okay? Then I'm going to distribute. I'm going to take u to the 4th times u, and u to the 4th times 1. So perhaps it would be a good idea to put parentheses around that binomial. So we would have u to the 4th times another u would be u to the 5th, and then minus u to the 4th times 1 is u to the 4th, and then du. All right, so now we can take the antiderivative term by term. So this is going to be equal to 1/9. I'm going to put some parentheses and rewrite and take the antiderivative of u to the 5th, which would be u to the 6th over 6, and then minus the antiderivative of u to the 4th is u to the 5th over 5. Close those parentheses, and don't forget, since this is an indefinite integral, plus c, so we've represented the whole family of functions that have the same derivative. So then the last thing we're going to do to simplify just a little bit more, let's distribute the 1/9. We'll multiply, here, let me show what we're going to do. We're going to take 1/9 times each term, and then also we're going to back substitute. These u's are going to be replaced with 3x minus 1. So our final answer then would be, I said minus 1, I meant plus 1. 3x plus 1 to the 6th power all over, remember we're taking 9 times 6, so that would be all over 54, and then minus, replacing u with 3x plus 1 again, that's to the 5th power all over, forgot my 1, to the 5th power, and then all over Now we're going to take 1/9 times 1/5, which would put a 45 down here in the denominator. And then don't forget your plus c. Final answer. So number 11 brings us to a definite integral. You know it's a definite integral because this time it has bounds. All right, so what's the difference between number 11 and the last few problems? Well, the last few problems were indefinite integrals, so the answers to all those problems were a family of functions with the plus c. When you're evaluating a definite integral, the answer is going to be a number or a value, all right? So for number 11, first of all, I changed this problem to make it a little bit less clunky. So this argument of pi over x, we're going to change that to x over 2. I think I told you that in class, but if not, go ahead and make that change now. So now let's decide, since this is a composition of functions, we have the outer function is the cosine of something and the inner function is x over 2. Let's go ahead and let u be that inner function. So I'm going to write it like this. I'm going to let u be, instead of x over 2, I'm just going to call it 1/2 x. That'll make it a little bit easier to find du. So du would be 1/2 dx. All right, so now when we talk about making substitutions, first of all, we can replace x over 2. Let's see, x over 2 I can replace with u, okay? And then the dx I can replace with du as long as I balance. Now, du is only half of dx, so to balance that out, we're going to put a 2 out front. So let's go ahead and do that so we don't forget. So we'd have 2 times, whoops, we'd have, oh, nuts, what am I doing here? We'd have, sorry, I'm having issues. Okay. Okay, so we'd have 2 times the integral of. Now, before you write bounds, we're getting ready to rewrite this integral in terms of u. So that means we need to make a change in these bounds. Right now, these are x bounds. This is an integral in terms of x, so these are x bounds. So what we need to do is rewrite our bounds in terms of u. So how do we make the conversion? Well, over here, we're told that u is 1/2 of x. So to get our u bounds, we just take these x bounds and put them in for x. So let's start by finding our lower bound. And when I say bound, I mean our lower limit of integration. Nuts, I can't spell bound. Just a second. Let me start over. Okay, get our lower bound. Lower bound. All right, so to get our lower bound, we're going to take 0, and we're going to replace it with x. So that would be 1/2 times 0, which is 0. So our lower bound stays 0. And then to get the upper bound, our upper u bound, then, we just replace, this time we replace x with pi over 2. So that would be 1/2 times pi over 2. 1/2 times pi over 2, which is pi fourths. So that's our upper bound. All right, so we've got the 2 out front to balance the fact that du is only half of dx, so we need to double the integral to make it balance out. Then we have our u bounds. Now, we're going to replace u with the yellow part with u, so this would be the integral of cosine u du. Whew. Okay, now we can find the antiderivative. So the antiderivative of cosine is positive sine. You might remember the little sine, cosine, negative cosine. In this little mnemonic device, you go down to derive and you go up to integrate. So if we're going to find the integral of cosine, it's going to be positive sine. So this would be 2 times, 2 times the sine of u, and we're going to evaluate that from 0 to pi fourths. All right, so that would be 2 times sine of pi fourths minus sine of 0, or 2 times, let's see, sine of pi fourths is square root of 2 over 2, and then minus sine of 0, let's see, on the unit circle, that's right here where the y value is equal to 0. So this is just going to be square root of 2 for our final answer. square root of 2, final answer. Number 12 is another definite integral, so that means and we know because we see these bounds, so we know that our answer is going to be a numerical value. So let's first of all decide what we want our u to represent or replace. So this inner function x squared plus 1 looks like a good choice. So let's let u be x squared plus 1, then du would be 2x. All right, so when we think about replacements then, we can substitute u in for x squared plus, whoops, need a highlighter. I guess that is a highlighter. Okay, so we need to replace all of this with u, and then the x dx, okay, the x dx can be replaced by du, except for the fact that du is 2 times too big. So to balance that out, let's put a 1/2, let's put a, having issues here, sorry. Okay, let's put a 1/2 out in front of that integral. Now, before we write the bounds, remember these bounds, 0 and 9, are x bounds, but we're about to rewrite this integral in terms of u, so they need to be u bounds. So let's talk about what our lower bound would be. So to get the lower bound, okay, we just take the lower bound of 0 and we put it in right here. So that lower bound would be 0 squared plus 1, or 1. So our lower bound, our lower u bound will be 1, and then our upper u bound, we're this time going to take 9 and put it in for x squared. So that upper u bound would be u equals 9 squared plus 1, which is 81 plus 1, or 82. So our new bounds go from 1 to 82 of, now, when we go to replace the yellow part, it's the square root of u, right? Square root of u. And it's also, which is the same as u to the 1/2, but it's in the denominator, so I'm going to rewrite that then as u to the negative 1/2 power. And then we're replacing x dx is getting replaced with du, which we can do because we have the 1/2 out front. All right, so now let's integrate. Let's find the antiderivative of u to the negative 1/2. So that's going to be u to the, now I'm going to do the work over here, and again, if you can fast forward this part if you want to, u to the negative 1/2 plus 1 over negative 1/2 plus 1. So let's talk about the coefficient first of all. Negative 1/2 plus 1 is equal to 1/2, and dividing 1/2 is the same thing as multiplying by 2. So we're going to have a 2 out front, u to the, and then we're going to take that negative 1/2 plus 1 again and get positive 1/2. So that's going to be 1/2, and we're going to evaluate that from 0 to 82. All right, so that's going to be equal to 1/2. Let's start some parentheses. We're going to have 2 times the square root of 82, and then minus, I guess I could do this, minus the square root of 0, which is just 0, okay? So all of that cleans up the one. Let's see, I hope you caught my mistake. Did you notice that I put 0 for this lower bound, and it should have been 1? So sorry about that. Let me fix that. Okay, so that means we're taking the square root of 1 here, okay? And then we can simplify this a bit. 1/2 times 2 is 1. The square root of 1 is 1. So our final answer then will just be square root of 82 minus 1. The next several problems in the review, you'll see integrands that are ratios or rational functions. So what you want to look for is if you can use that natural log rule. Remember, the integral of 1 over x dx is the natural log of the absolute value of x plus c. Now, if the denominator, instead of just being x, if it's a function of x, then if it looks like this, the integral of u prime over u dx, all right, in other words, if the if the numerator is the derivative of the denominator, then the answer would just be the natural log of that the natural log of the absolute value of that denominator plus c. So let's take a look at the first one and see if that's the case. Well, the denominator is a function of x plus 7. The derivative of that would be 1. So, in other words, we could take this 3 and pull it out in front of the integral, and we'd have 1 over x plus 1. So we have u prime over u. So that means that makes this a very simple problem. It's just going to be 3 times the natural log of the absolute value of that denominator, x plus 7, and then don't forget your plus c. And then just a reminder of how that worked out. We pulled the 3 out in front, okay, which would make this 1 over x plus 7. So that means that the numerator was the derivative of the denominator. It was u prime over u. So that means we can just take the natural log of the absolute value of the denominator plus c. All right, and then number 14, this was not quite so straightforward. It's almost u prime over u. The derivative of the denominator would be 2x, and this is x. So why don't we just rewrite this slightly? Let's rewrite this integral like this. 1/2 the integral of 2x over x squared minus 1 dx. All right, so do you see what we did? We multiplied 1/2 times 2. That's just 1. Those cancel each other out. So by rewriting it this way now, the numerator is the derivative of the denominator, so our answer is just going to be 1/2 the natural log of the absolute value of that denominator, x squared minus 1 plus c. Now I want to mention you also could have done u substitution on this problem. Just let u be x squared minus 1, and then once you back substitute, you get the same answer. Okay. And then the first of two numbers, 15, I guess it was the number so nice I used it twice. So our first number, 15, first of all, I just want to clarify, in case there's any misunderstanding, the argument of sine is just the theta. So this is sine theta plus a constant. So what that means is this problem is in that u prime over u situation, because the derivative of the derivative of sine u is cosine u, and the derivative of this constant, pi divided by 2 would be a constant, would be 0. So since the numerator is the derivative of the denominator, then we can use our natural log rule, and our answer is just going to be the natural log of the absolute value of the denominator, which is sine theta plus pi halves, and then don't forget your plus c. So in our second number, 15, this time there's no way the numerator is the derivative of the denominator, so it's not a u prime over u. And you'll notice that when you see a ratio that looks like this, a big old polynomial on top, and the denominator is in that form x minus c, where we can call x plus 1 x minus c. It's x minus a negative 1, right? So it's in that form x minus c. This is where we want to use either long division or synthetic division to rewrite the integrand. So I'm going to use synthetic division just because it's quicker. You're welcome to use long division as well. So for synthetic division, remember the setup for it is, I just erased that. Remember, this is x minus c, x minus a negative 1. So you want to put c in the little box. So we're going to put a negative 1 in the box. Then we put our coefficients in a row. Now let's see if we have any powers of x missing. It goes x squared, x to the first, and then our constants. So we don't need to add any coefficients. So I'll write those coefficients, 1, 3, and then we put our constant term, leave some space, bring down the first coefficient below the line, and then this little box right here, this is where your remainder is going to end up. All right, so then to do synthetic division, we start by taking, I have my negative 1 as part of the box. Let me fix that. So negative 1 in the box. All right, so we start by taking negative 1 times 1 which is -1, which we write right here. Then your next step is to add. This is different from long division. You add this next step. So we take 3 plus -1, which gives us 2. And now we're going to multiply, start the process over again. -1 times 2 is -2. So we'll write that here. And then we'll add 5 and -2 and get 3, which is our remainder. So remember, your quotient, your answer is going to be 1 degree lower than the dividend. You're dividing an x squared by an x, so this should be 1 degree lower. So that means our quotient is, this is our first coefficient, which is 1, would be the coefficient of your x term. And then this is going to be the constant, and this is going to be your remainder. So it would be, our quotient then is x minus 2. And then since we have a positive remainder, then we would write plus the remainder over the divisor, which is x plus 1. All right, now that is our new integrand. So now let's go ahead and find the integral going term by term. So the antiderivative of x is x squared over 2, and then minus the antiderivative of 2 is 2x, and then this next term, if we pulled the 3 out front, then we'd have 3 times 1 over x plus 1, so we have u prime over u. So the integral of that then would be plus the natural log of the absolute value of that denominator, x plus 1. Oh, I forgot my times 3, so let me fix that. I think I'm going to have to erase. Let me rewrite that. Remember, we pulled the 3 out front, so this would be plus 3 times the natural log of the absolute value of x plus 1, and then don't forget your plus c. For number 16, you should notice a pattern here. When you see this radical in the denominator and you have a number, a constant minus a function of x squared, that's going to be an integral that involves inverse sine, or sine inverse, or arc sine. So if it fits this pattern, the integral of du over the square root of a squared minus u squared, then that antiderivative is arc sine, or sine inverse, of u over a and then plus c, since this is an indefinite integral. Okay, so let's take a look at our problem here. This is a squared, which means a would be 3, and then this function 25 squared is our u squared, so that means u is 5x. Now, since u is 5x instead of just x, that means du would be 5 times dx, so we're going to have to balance this out with that 1/5 out in front of the integral. So this would be equal to 1/5 arc sine of, what was u? U was 5x, oops, I missed it, is 5x all over a was 3, and don't forget about your plus c. And then number 17, you'll notice that it fits the pattern of the integral of du over a squared plus u squared. So its antiderivative is 1 over a arctan, or tangent inverse, of u over a plus c. So number 17, our a squared is 5. That means that a is the square root of 5, and then u would be x. So the antiderivative then would be 1 over a, or that would be 1 over the square root of 5, times tangent inverse, or arctangent, of u over a, which would be x over the square root of 5 plus c. In number 18, we're going to complete the square so that we can make it look more like this pattern, where we have an a squared plus u squared, a constant squared plus a function of x squared. So this trinomial is almost a perfect square. The only problem is this 31 kind of messes it up. So here's how we're going to fix it. look at your first two terms and let's make that binomial into a trinomial that's a perfect square. So what we do is we take the coefficient of x, we're going to take half of that coefficient and square it. So this would be equal to the integral of dx over x squared plus 10x. Now we're going to add half of the coefficient of 10 and squared. So half of the coefficient of 10 is 5, and 5 squared is 25. So plus 25. So we've just created a trinomial that's a perfect square. Now don't forget about the plus 31 that was already there. So plus 31, and then to balance things out, I can't just add 25, but if I at the same time subtract 25 in that denominator, then we're fine. Okay, so we can rewrite this then as the integral of dx over x squared plus 10x plus 25. I guess I'm taking an extra step here that's not necessary. And then that 31 minus 25 is 6 plus 6. Okay, so this is our trinomial that's the perfect square. So we're going to go ahead and factor that. So we would have the integral of dx over that x squared plus 10x plus 25 factors into x plus 5 squared plus 6. So now we've got this in the right form where we can use the integral involving arctangent, where x plus 5 is going to be our u, and then the 6 is, well, this is u squared, and 6 is a squared. So in other words, u is x plus 5, and a would be, since a squared is 6, a is the square root of 6. Okay, so now our final answer, if we put it into the formula for integrals involving arctangent, our final answer is going to be 1 over a, so that would be 1 over the square root of 6 times arctan. You can either write arctan or you can write tangent inverse, it doesn't matter. Arctan or tangent inverse of u over a, so that would be x plus 5 over a over the square root of 6, and then don't forget your plus c. Number 19 has many parts to it, so let's get started. First of all, we're going to let g of x be this function, the integral from 0 to x of f of t dt, where f is the function whose graph is shown. So let's just go ahead and identify this is the graph of f that we're looking at. Okay, so the first thing we're asked to do is to evaluate g of 1, g of 3, g of 4, g of 6, and g of 7. So let's do that real quick. So let's start with g of 1. So g of 1 would be the integral from 0 to 1 of f of t dt. So what does that mean? That means the area of between the graph of f of t and the x-axis. So if you look at the graph from 0 to 1, we're talking about this area that's below the x-axis. So its area is 1/2, but the value of this integral is going to be negative 1/2 because we're talking about a region below the x-axis. So that's equal to negative 1/2, all right? And then g of 3 would be the integral from 0 to 3 of f of t dt. Do you see what we're doing? We're just evaluating, we're just replacing g of x is 0 to x of f of t dt. So g of 3 would be the integral from 0 to 3 of f of t dt. So we need to look at this graph and determine what is the area from 0 to 3. So this area has a positive, that's a triangle whose area would be 2. But we need to subtract this negative area here. I say negative area, but I mean area whose integral is negative. So this would be, let's see, 2 minus 1, that would be 1/2. So g of 3 is 1/2 or 1.5. Doesn't matter whether you write it as a fraction or a decimal. And then g of 4, the next part would be the integral from 0 to 4 of f of t dt. Okay, now if we look at the whole thing from, from 0 to 4, remember 0 to 3 was 1.5, and then 3 to 4, this area right here is half of a rectangle that has an area of 2, so that's just one more. So that would be 2.5, or if you want to write it as a fraction, it'd be 5 halves. So this would be 2.5 or 5 halves. All right, then next we need g of 6. G of 6 would be the integral from 0 to 6 of f of t dt. Okay, so, oops, I have an extra parenthesis there that I don't need. Let me fix that. Okay, so we're going to take the area from, let's see, from 0 all the way to 6. So remember, the area from 0 to 4 was 2.5, and then this is a semicircle. Remember, you find the area of a semicircle by taking pi r squared. Well, this would be a circle whose radius is 1, but we only want half of that circle, so we're going to divide by 2. So this area is, let me shade it in. So this area is pi halves, but since it's under the x-axis, its integral value is negative pi halves. So that means g of 6 would be 2.5, and then minus pi halves. All right, and then g of 7 would be the integral from 0 to 7 of f of t dt. So all we need to do is take what we have so far, which is 2.5 minus pi halves, and then we just need to add this extra area of 1/2. So that means the integral from 0 to 7 of f of t dt would be 3 minus pi halves. All right, and then these next several questions, you might want to take a look at your calculus house notes and be able to recreate that calculus house if necessary, because it's just a review of those kind of questions. Letter B says, for what values of x is g increasing from 0 to 7 and decreasing from 0 to 7? And then be sure to justify your answer. So let's start with the integrals where g is increasing. Well, if you look at your calculus house, g is increasing wherever f is positive. Oh, and let's also make a note. The graph of f is also the graph of g prime. Okay, if we take the derivative of g, we're going to get f. So when you look at the graph of f, you're also looking at the graph of g prime. So these questions that you're answering about the function g, you're basing them off of the fact that you're looking at the graph of g prime. So where is g increasing? G is increasing wherever g prime is positive. So it's positive from 0, no, not 0, sorry. It is positive from 1 to 4, and then again from 6 to 7. So g is increasing on 1 to 4 and on the interval from 6 to 7, and our reason is because g prime is positive. Okay, and then where is g decreasing? Well, g is decreasing wherever g prime is negative. So g is decreasing from 0 to 1 and from 4 to 6 because that is where g prime is negative. All right, and then letter C says find, and letter C we're going to find the x values on the open interval from 0 to 7 where relative extrema occur. So as you look at the graph of g prime, relative extrema occur where g prime crosses the x-axis, where it goes from negative to positive or positive to negative. So it looks like we have at 1 and at 6, g prime is going from negative to positive, so those are going to be relative mins, and then we'll have one relative max right here at 4, where g prime changes from positive to negative. So let's write out that response and a justification. So we're going to say that g has a relative min until where it happens at x equals 1 and x equals 6, and the reason is because g prime changes from negative to positive, and then g has a relative max at x equals 4 because that is where g prime changes from positive to negative. All right, and then letter F, okay, says find the absolute maximum on this closed interval from 0 to 7 and the values of x where that maximum occurs, and justify your answer. Now, our justification is just going to be a candidates test. All right, so what are the candidates for an absolute maximum of g? Well, the candidates are the endpoints and then also any critical points. Critical points would be where g has a max or a min. So those would be on, as you're looking at the graph of g prime, that would be wherever we have zeros. So our candidates for our candidates test are going to be the endpoints 0 and 7, and then 1 and 4 and 6, because those are where we have critical numbers. All right, so let's make our table for our candidates test. So we'll have x and then g of x. Okay, so what are our candidates again? They are the endpoints and then the critical numbers. And those critical numbers happened at 1 and at 4 and at 6. All right, so g of 0. Now, we didn't evaluate that earlier, so let's talk about it really quick. The integral, if we're going to evaluate g of 0, we're going to take the integral of 0 to 0 of f of t dt. Well, that means that we're talking about a region that has no area at all, so that's equal to 0. So that probably won't be our max, but we don't know until we've looked at all the candidates. G of 1, if you look up earlier, we already figured that out. That was negative 0.5. Okay, G of 4 we found earlier to be positive 2.5. G of 6 was 2.5 minus pi halves. And then G of 7 was 3 minus pi halves. All right, so we got to think about this, about which one of these, we're looking for a relative absolute max, so which one is the biggest value? Well, remember pi, let's see, pi is 3.14, right? So if I divide that by 2, I'm going to roughly call that's very approximately equal to 1.5, isn't it? Because 3 divided by 2 would be 1.5. So that means 2.5 minus 1.5 is only 1, and 3 minus 1.5 is 1.5. So it looks like this is our winner here. This is our max. So let's circle it. We've identified our absolute max. And so now let's answer the question. It says find the absolute max and the value of x where it occurs. So we need to say, and it is a max of the function g, so we need to say our function g has an absolute max of, let's say what that max is, it's of 2.5, and then let's say where it occurs, and it occurs at x equals 4. All right, and then last but not least, for number 19, we need to write an equation of the line to the graph of g that's tangent to the graph of g at x equals 3. So as always, when we're writing the equation of a line, start with point slope form. Y minus y sub 1 equals m times x minus x sub 1. So the three things we need to find are an x1, a y1, and a slope at x equals 3. So we have our x1. X1 is 3, okay? So now what is y1? Well, y1 would be whatever g of 3 is. Now, did we do that earlier? Let's look up here. G of 3, remember, was 1.5. So we have our g of 3. That's our y1. And it was, what was it, 1.5? Okay, 1.5. And then the last thing we need is m. We need the slope of the line tangent to the graph of g at x equals 3. In other words, what we're looking for m is we need g prime of 3, don't we? So let's look at our graph of g prime and then just see what the y value is when x is equal to 3. So looking at our graph of g prime, when x is 3, g prime of 3 is 2. So that's our slope. All right, so we have our slope. Let me indicate that. That is 2. So now we can write our equation. So the equation of the line would be y minus 1.5 equals our slope of 2 times x minus x sub 1, which is 3. All right, so now let's move on to the calculator portion of our review. For number 1 in our calculator portion, we're given that g of 4 is 7 and that g prime of x is sine of x over 2, and we're asked to find g of 15. So before you touch the calculator, you might want to write down symbolically what we're being asked to do. Well, we're being asked to find g of 15. So g of 15 would be equal to the initial value, which would be g of 4, plus the change, which would be the integral from 4 to 15 of g prime of x dx. Or, in other words, we're being asked to find g of 4 is 7 plus the integral from 4 to 15. We're told that g prime of x is sine of x over 2 dx. And now it's time to grab your calculator and go to it. So what you're going to punch in is you're going to punch in 7. And then to get this, remember you want to type math 9. That's if you're using a TI-85. Hit math 9, and I think it'll be obvious what to type in. Don't forget you need to type in this final x. And then when you hit enter, you'll get your answer. And usually you're being asked to give your answer correct to 3 decimal places. So what you can do to avoid any rounding error is just copy the first 4 decimal places. So if you do that, you would get 5.4744, and then just truncate or chop off the rest of the decimals. Don't worry about any rounding, and just leave your answer like that. Okay? Then number 2 says, we have a particle that moves along the x-axis with a velocity of v of t equals the square root of 1 plus e to the t. Try to get this, sorry. There we go. 1 plus e to the t. Find the particle's motion at time t equals 9 if s of 1 equals negative 1. Well, s is our position function, velocity, and v is our velocity of function. So remember, velocity is the derivative of position, or we can say that the other way, position is the antiderivative of velocity. So if I want to see a change in position of an article, if I want to see its final position at time t equals 9, what we're being asked to find is s of 9. So s of 9 would be the initial condition, or the initial position, which is s of 1, plus the integral from 1 to 9 of v of t dt. Okay, so that would be our initial position, and then if you integrate, velocity is a rate, if you integrate this rate, you're going to get the change in position. So what are we going to type into our calculator then? S of 1 we're told is negative 1, and then we're going to type the integral from 1 to 9 of the square root of 1 plus e to the t dt. Now, on your calculator, these are going to be x's, right? You'll replace those with x's. So punch that in, and then be sure and copy down the first 4 digits, and when you do, you should get 176.3154 for your final answer. Number 3 tells us that a salt truck leaves the garage with 576 pounds of salt. When the truck starts spreading salt on the road, the amount of salt in the truck decreases at a rate of h of t equals negative 7.75 e to the 0.02 t, where t is measured in minutes. So this is a rate function. Then it says how much salt remains in the trunk after the first 3 minutes of spreading salt. Okay, so let's write symbolically what we're being asked to find. What we're being asked to find is the amount. Now, if little h of t is the rate at which the salt is leaving the truck, let's call capital H of t our amount function. So, and what we're being asked to find is h of 3, the amount of salt in the truck after the first 3 minutes of spreading salt. So, to find that, we're going to take the initial amount, which would be h of 1, plus the change. Now, to find the change in the amount of salt in the truck, we're going to integrate the rate at which it's leaving. So, we'll integrate from 1 to 3, little h of t dt. All right? So, little h of t dt is the rate at which the salt is leaving the truck. So, to find h of 3 then, we're going to take h of 1, which is the initial amount of salt in the truck, which was that 576, plus the integral from 1 to 3 of negative 7.75 e to the 0.02 t dt. So very carefully punch that into your calculator. Just remember these t's are actually going to be x's when you punch it, because that's what the variable that the calculator uses. Be really careful when you're typing in that you don't make a typing error. There's lots of little decimals and negatives and all that, so just be careful typing it in. And when you do and get an answer rounded, well, we're not going to round, we're going to go out to 4 decimal places. You should get 552.0383 for your answer. Now, what does that mean? It doesn't really have any meaning until we give it a unit. So what is that? Let's think about that woo-woo. What is that? That would be pounds of salt. So pounds of salt that would be left in the, I'm going to write a space here, I'm going to write it down here, in the truck. And then that was the watt with units, pounds of salt left in the truck. And then let's say the when, let's say at t equals 3 minutes. All right, so likely on the test, I will ask you to interpret your answer and give it some meaning like that. Okay, then number 4, our last calculator question. Let's take a look at that. So I'm going to erase some of this extra stuff. Okay, number 4 says the following. It says we have a 300-pound ice sculpture that's melting, and the rate in pounds per hour at which the amount of ice decreases is given by little m of t. The table below indicates the rate at which the sculpture is melting at various times from noon to 6. So let's talk about what this means, what these numbers mean. M of t is a rate function. It tells you at a certain, for each of these times, it tells us how many pounds per hour, the rate at which the ice is melting. So for example, at noon, at that instant, the ice was melting at negative 1 pounds per hour. At 3 o'clock, it was melting at negative 9.44 pounds per hour. Since this rate is negative, obviously the amount of ice was decreasing. Okay, so letter A says estimate the number of pounds of ice remaining in the sculpture at 6 o'clock using a Wright-Riemann sum, and then determine if it, now the it that we're talking about is the Riemann sum, is an overestimate or an underestimate. Now, one thing I neglected to tell you is how many subintervals. So let's go ahead and let's use 6 subintervals. All right, so to get if we were going to get an exact amount of ice left in the sculpture, we would take the initial amount, which was 300 pounds, plus the integral from 0 to 6, because if we let noon be t equals 0 and 6 o'clock be t equals 6, it would be the integral of m of t dt. Now that would give us the exact amount. Unfortunately, we don't yet have a function for m of t, the rate at which the ice is melting. So what we're going to do is we are going to estimate this integral with a Wright-Riemann sum with 6 subintervals. So let's just review how quick to do that. If we're going to have 6 subintervals, 1, 2, 3, 4, 5, 6, notice that delta x every time is 1, noon to 1, 1 to 2, 2 to 3, and so on. So delta x is 1, and then the height of the function, the height of those rectangles would be these function values. So, in other words, to get that estimate, we're gonna, let's just say this is approximately equal to 300 plus. Now let's get that Wright-Riemann sum. So, since we could write negative 1 times delta x is positive 1. So we could write positive 1 times negative 1 plus positive 1 times negative 2.11 plus positive 1 times negative 4. So what I'm going to do is I'm just going to factor out that 1, okay, since delta x is the same. Now, if delta x changed, we couldn't do this. But since delta x is the same for every rectangle, I'm just going to say 1 plus the right values. Now, since it's a Wright-Riemann sum, we're going to start at this first rectangle, take this right-hand y value will be our first one. So that's going to be negative 2.11, then plus negative 4.48, then plus negative 9.44, and so on. 97, negative 42.22, and then plus negative 89.26. Now, since this is the calculator portion of the test, or the review, you'll grab a calculator, you'll do that arithmetic, and you should get, this would be, I'm running out of room here, 300, that was my initial amount, 300, and then plus negative 167.48 for a final answer of 132.52. So let's talk about what that number means. All right, that number is, first of all, it's the number of pounds of ice that is remaining. So let's write this down. So there's 132.52 pounds of ice in the sculpture. So that's the watt with units, and then the when would be time equals 6 o'clock p.m. Now, if I say 6 o'clock p.m., that's saying that 6 hours has gone by. All right, now, is that an overestimate or is it an underestimate? Well, since this is a decreasing function, obviously it's a decreasing function because the ice is melting, so the amount of ice is decreasing over time. Remember, a right Riemann sum, let me just draw a quick picture. Here's a decreasing function. Let me draw a right rectangle, okay? So you can see that that's going to be an underestimate. So, I don't have room to write my answer. I'm just going to make a little box here and say it's an underestimate because our function, well, I should have given the amount function a name. Let's go ahead and call it, if little m of t is our rate function, let's call capital M of t the antiderivative, which would be the amount function. So we'll say because m of t is decreasing. All right, and then letter B, now we're given a function for the rate at which the ice is melting. It says if m of t is negative 2 to the 1.08 t, find the exact number of pounds in the ice remaining in the sculpture at 6 o'clock. So now that we have a function, we can find the exact amount of ice. So let's let capital M be that amount function. So capital M of 6 would be equal to the initial amount of ice, that would be capital M of 0, plus the integral from 0 to 6 of little m of t dt. So these are capital M's. Make it a little more obvious than this is a little m. Okay, so that would be equal to, well, m of 0 is the initial amount of ice, so that's 300 plus the integral from 0 to 6 of negative 2 to the 1.08 t dt. So grab a calculator and punch that in, and you should get 182.0949, and then let's interpret that answer. That would be pounds of ice left in the sculpture, so that's the watt with units, pounds of ice left in the sculpture, and then the when would be at 6 o'clock p.m. Or you could say at t equals 6 hours. That would be fine also. Okay, and so let's take a look at letter C. Our last question, it says, we're given that rate function again, m of t equals negative 2 to the 1.08 t power. Now, I think there's a typo here. I said find the average amount of decrease of ice in pounds per hour. So did I mean to say amount there? No. What I meant to say was rate. So let's fix that. We're going to find the average rate of decrease of the ice in pounds per hour from noon to 6. So to find that average rate, we're going to take, well, let me just write in general what we would take. 1 over b minus a, the integral from a to b of our rate function, which is m of t dt. So in this case, it would be 1 over b minus a. Well, that would be 6 minus 0, or just 1/6, the integral from 0 to 6 of negative 2 to the 1.08t dt. All right, so you'd punch that into your calculator. You would get an answer. Now we're going to round that. We're going to go out to 4 decimal places and truncate, and we would get negative 19.6508. So now let's interpret what that means. So what that means, what we were asked to find the average rate of decrease of the ice in pounds per hour. So let's write our interpretation like this. We'd say the amount of ice is, and let's use the word changing. I don't want you to use decreasing here, because let's let the sign of the rate tell us whether it's increasing or decreasing. So let's say the amount of ice is changing and now remember this was asking us for an average rate. So at an average rate of negative 19.6508, and the units would be pounds per hour. So that's the watt. The watt is the amount of ice, the rate of change of the amount of ice in pounds per hour, and then the when with units would be from t equals 0 to t equals 6. All right, so hours, don't forget the unit. All right, so that brings us to the end of our Great Big Giant review. I hope this has been helpful. If you have any more questions, be sure and come see me or email me, or we should have a few minutes to answer questions before we get going on the test. And I just want to wish you the best of luck on your test.